My next structure is the ammonium ion, NH4+, and remember that this is an ion, so once we add up the total number of valence electrons, we'll need to correct that number based on the fact that we have a positive charge. So my atoms for this structure are that I have a nitrogen and I have hydrogen. So in this structure I have a nitrogen and I have 4 hydrogens. My nitrogen will contribute 5 valence electrons to the structure, and I have 4 hydrogens that will each bring 1 valence electron to the structure. That gives me a total of 9 electrons. This is not my final total, 9 electrons. This is not my final total because I have a positive charge that I need to account for. Remember, my positive charge tells me there's one more proton in the nucleus than electron, so that means that I need to subtract an electron to correct for that charge, and my new working total of electrons is going to be 8. I have exactly 8 electrons to put into this structure. So as I follow my rules, when it comes to my central atom, my best candidate is the nitrogen. So my nitrogen goes in the middle, and I'm going to bond my 4 hydrogens to it. In doing so, I use 2, 4, 6, 8 electrons, which are all the electrons I have, so I'm out of electrons. This is almost the correct Lewis structure for this molecule because I still have to include the charge. Whenever I have a Lewis structure that has a charge, one way that I can convey that charge information is by placing this structure in brackets with the charge outside. There's another way that you can convey the charge information, that's formal charge, and we'll get to that a little bit later on. So this is the correct Lewis structure for the ammonium ion. Our next example is the nitrate ion, NO3-. Pause the video and go ahead and try to complete the structure of the nitrate ion. So if we look next at the example of the nitrate ion, this ion contains nitrogen and oxygen atoms. My nitrogen brings 5 valence electrons to this structure, and I have 3 oxygens that each bring 6 valence electrons to this structure, giving me a total number of electrons of 23. Because this is an ion, I know this is not my final electron count. Because this is an anion, this means that I have one more electron in my structure than proton. So 23 is the number of electrons that would be in this structure if I had a neutral atom. Because I have that negative charge, I need to add in one more electron because of that negative charge, and my total number of electrons is then 24. 24 is my working number of electrons. 24 is exactly the number of electrons that my structure must account for. So as I continue to follow the rules, my best candidate for a central atom is the nitrogen, based on it being less electronegative than the oxygen. So if I put the nitrogen in the middle of this structure and bond my 3 oxygens to it, I get a structure that looks like that. Placing my atoms into the structure in this manner used 2, 4, 6 electrons. So if I subtract those 6 electrons from my 24 electrons, I have 18 left. Rule number 3 then tells me to complete the octets for my outer atoms. So that means I'm going to give this oxygen 6 electrons. This oxygen currently sees 2 electrons in the form of a single bond, so that if I give the oxygen 6 more electrons, I complete its octet. I'm going to do the same thing for my other 2 oxygens. And by giving 3 oxygens each 6 electrons, I used my remaining 18 electrons, and I'm out. As I continue to follow the rules for this structure, there are no additional electrons to place on my inner atom. And in Rule 5, when I look at my central atom, I see that my nitrogen does not have an octet. My nitrogen currently sees 2, 4, 6 electrons, and it's looking to get 2 additional electrons in the form of a double bond. So just as I did before, I'm going to look to my outer atoms for additional electrons. But what I find is that in this case, as I look to my outer atoms, my nitrogen has an outer atom here with additional lone pairs that it can share, an outer atom here with additional lone pairs that it can share, and an outer atom here with additional lone pairs that it can share. So I have a total of 3 oxygens that are capable of making that double bond with the nitrogen. So my 3 oxygens that have lone pairs are going to be able to each share additional electrons with the nitrogen to form a double bond, and that's going to result in a total of 3 possible Lewis structures that I can end up with. If I first look at the oxygen here on the left, this oxygen has 3 lone pairs, and if this oxygen shares this lone pair with the nitrogen, that's going to give me this structure here, which I will call A, where this oxygen used its lone pair to create that double bond in the structure. So if I look at my oxygen that points down, this oxygen has 3 lone pairs that it could share. If I take this lone pair and share it with the nitrogen, that's going to give me a nitrogen-oxygen double bond that points down, like this structure here, where these 2 oxygen-nitrogen bonds remained untouched. This oxygen that points down in the structure now gives me my double bond, and I'll call this structure B. If I look at my third oxygen, the one that points to the right, this oxygen also has 3 lone pairs that it could share with the nitrogen. So if I take one of those lone pairs and give it to the nitrogen, that's going to give me this structure here, which I'll call structure C. And in this structure, I have my nitrogen-oxygen double bond pointing to the right. Overall, because I had 3 outer atoms that had lone pairs that could share with the nitrogen, there were 3 ways that I could complete this Lewis structure. Notice that each of these structures for the nitrate ion that follow my rules for Lewis structures, I have each of them in brackets with the charge outside, giving me my complete structure for each of these. The 3 ways that I can complete this Lewis structure give rise to a concept that's called resonance. The relationship between structures A, B, and C is that they are resonance structures of one another. And more specifically, A, B, and C are also equivalent resonance structures. The fact that they are equivalent resonance structures is why you look at the structures and wonder why we need to know that there's 3 ways that we could form that structure. The fact that I have 2 single bonds and 1 double bond between my nitrogen and my oxygens in A, in B, and in C, because I have that same bonding pattern, that's how I have equivalent resonance structures for the nitrate ion. Resonance is a very important concept, especially as you go on to organic chemistry, and we're going to talk a lot more about resonance structures in the next video.